Hi, I'm Catherine Messick from Los Alamos National Lab. This talk is about the development of a low-resource combined gamma-ray and neutron spectrometer for planetary science. I'll first provide a brief overview of planetary nuclear spectroscopy. Then I will talk about the EPICS instrument concept that's under development at LANL. Then I will show some simulated performance of EPICS for two notional mission concepts, and then I will summarize. And I'd like to acknowledge my co-authors and the LDRD program of Los Alamos for funding this research. If you are not familiar with planetary nuclear spectroscopy, the bottom line is that it provides unique signatures of elemental and volatile abundance on planetary bodies. Most commonly, this technique has been used on airless bodies like the moon or asteroids, or near airless bodies like Mars, which has a very thin atmosphere, where galactic cosmic rays can strike the surface, break up nuclei within the surface, and generate spallation neutrons. Those spallation neutrons then further interact in the surface, generating neutron and gamma-ray albedo signatures that are reflected back out of the surface and detectable by instruments on the surface or in orbit. And this is illustrated in this cartoon. The neutron energy spectrum that comes out of the surface is related to the amount of moderation that has occurred. For example, neutrons have a high cross-section for interacting with hydrogen, and therefore measuring neutrons coming out of the surface is extremely sensitive to the presence of hydrogen. Gamma rays are generated from different interactions such as neutron inelastic, neutron capture, or just the radioactive decay of natural elements such as potassium, uranium, and thorium. The gamma rays are emitted at characteristic energies, which means that you can look for specific energy gamma rays in your spectrum and be able to detect the presence and abundance of, for example, iron, magnesium, or silicon. You can also use a pulsed neutron generator to actively interrogate the surface, resulting in similar neutron and gamma ray albedo signatures. And this allows this technique to also be used on planetary bodies with a thick atmosphere like Venus. And nuclear spectroscopy is most sensitive to the top meter or so of the surface, which is unique compared to some other instrumentation that is used for planetary science, like infrared spectroscopy, which is very superficial, or radar, which is much deeper. This table shows some of the previous and upcoming missions that have included or will include nuclear spectroscopy instruments, starting with the Apollo missions back in the 1970s, including gamma-ray spectrometers. There's been a range of target bodies from the inner solar system and with measurements at Mercury out to upcoming measurements from the Dragonfly mission. That's the most recently selected New Frontiers mission, which will be visiting one of Saturn's moons, Titan. There's also a variety of international agencies that have fielded missions that have included nuclear spectroscopy instruments. Some of the questions that nuclear spectroscopy can help address are the search for extraterrestrial life through the detection of water, for example, or other elements that are considered to be essential for the formation of life, planetary structure, origins, and evolution, and planning for human exploration by in situ resource utilization, so looking for hydrogen, fuel materials, etc. And I also want to point out that on this list, the majority of these missions have all been fairly large missions, from Discovery class up to flagship orbiter-like missions to large rovers like the Mars Curiosity rover. The only one to my knowledge that has been a CubeSat mission that's upcoming is the Lunar Polar Hydrogen Mapper mission, which is launching next year. And so these missions have typically employed separate gamma ray and neutron instruments. They may share some components like an anti-coincidence shield or electronics. The gold standard for neutron detection has been helium-3 proportional counters, such as Lunar Prospector, which is shown in the upper right. It had two helium-3 tubes, one covered with cadmium to detect only epithermals. Cadmium blocks neutrons below 0.4 eV, or electron volts. So you end up with two energy bands, detectable thermal and epithermal. Boron-loaded plastic, lithium glass, and steel beam have all also been used. For gamma ray detection, the gold standard has been high purity germanium, which provides exquisite gamma energy resolution, but it does require cryocooling and frequent annealing. And so the messenger gamma ray spectrometer shown in the lower right had a high purity germanium crystal that can be seen in the middle, and the surrounding material is largely the cryostat. There have also been scintillators like BGO and cesium iodide, which have about 10% energy resolution at 662 keV full width half max. And these detectors have typically been bred out with photomultiplier tubes, which are bulky, susceptible to magnetic fields, and require kilovolt scale bias. And as I mentioned on the previous slide, the NASA missions that have flown these instruments before have been Discovery class to flagship orbiter missions, with the exception of the upcoming CubeSat mission, LunaMap. So that comes to the El Paso Light Planetary Ice and Composition Spectrometer, which is a low resource combined neutron and gamma ray spectrometer that's under development at LANL. It utilizes two relatively new technologies, El Paso Light scintillators and silicon photomultipliers, which I'll talk about more on upcoming slides, to reduce size, weight, power, and instrument complexity. It's designed to be a modular instrument that can be scaled for mission requirements and hopefully provide flexibility that allows it to be utilized on lower resource missions such as small sat missions. An orbiter-sized version shown in this rendering on the right is a 4-module version of EPIX with this estimated weight, power, and size. That corresponds to about 45% less mass and 35% less power than the messenger gamma ray and neutron spectrometer, which flew to Mercury, and about 25% less mass and 8% less power than the Dawn Grand gamma ray and neutron spectrometer, which went to the asteroids Vesta and Ceres. EPIX does have significant heritage in terms of the components. The scintillator that's used in EPIX has undergone thermal characterization, radiation damage assessment, has been tested on the high altitude balloon, and is the scintillator used in the LunaMap CubeSat mission that's upcoming in a launch next year. However, they only utilize the neutron capability of this particular scintillator, which I'll show does have the ability to also detect gamma rays. Silicon photomultipliers have undergone thermal characterization, radiation damage assessment, and have actually flown on the SDP Sat-5. And the scintillator, SIPMs, and processing electronics are all part of an upcoming LANL experiment that will launch on SDP Sat-6, also hopefully next year. The scintillator that is used in EPIX is an El Paso Light scintillator called CLIC. That's cesium lithium yttrium chloride. El Paso Lights are inorganic scintillators that can detect both gamma rays and neutrons in the same detection volume, utilizing pulse shape discrimination to distinguish between the two. That's illustrated on the plots on the left. So the top plot on the left shows the scintillation light output for incident gamma rays in blue and neutrons in red. And you can see that they're very different, which means that you can integrate different regions of the scintillation light profile in time and generate a pulse shape discrimination ratio, which is shown on the y-axis in the lower left plot, versus energy. And here you can see that the gamma ray band is clearly separated from neutrons, which are detected through neutron capture on enriched lithium-6 within CLIC. On the right, the rendering shows a single module version of EPIX with a cutout so that you can see the different components. On the side that faces the planetary surface, there's a thin 6 millimeter thick El Paso Light volume of CLIC that's used for thermal neutron detection. Then there's a cadmium layer that blocks thermal neutrons from entering the central CLIC volume, which is 5 centimeters on each side. And that's used for epithermal neutron detection and gamma ray spectroscopy. And then on the other sides, there is a plastic scintillator, which is used as an anti-coincidence shield to reject charged particle backgrounds and can be used as a fast neutron tag where the fast neutrons will scatter in the plastic and then capture in the central CLIC volume. So one of the challenges that we had to face was using silicon photomultipliers to read out a large CLIC volume. But first, you can see on the pictures on the left side how much reduction in size you can achieve by using silicon photomultipliers. You see a big PMT versus the compact silicon photomultiplier array. And also, silicon photomultipliers only require tens of volts bias instead of kilovolt scale bias. But one of the challenges of using arrays is that if you're doing pulse shape discrimination, you can't just sum the array elements together because you'll degrade your pulse shape information. And so we had to design a amplification and summing circuit that would preserve pulse shapes, which you can see in the figure in the middle. We also were able to achieve PMT-like performance in terms of the figure of merit that we measured, 3.6, which is excellent, and the energy resolution. And we also were able to measure iron lines at 7.6 MeV, demonstrating good linearity of our system up to high energy, which is shown in the lower right picture, where you can see there's an iron doublet, and you can see the single and double escape peak as well. So one of the notional mission concepts we simulated was a small planetary body surveyor, like an asteroid rendezvous mission. You can use the gamma rays to detect key elements to help determine the composition of planetary bodies, or primitive bodies, which is illustrated on the right. This shows the iron to silicon on the Y versus iron to oxygen ratio on the x-axis. The top panel shows compositions from a meteorite database for 3 different types of asteroid compositions: carbonaceous, achondrite, and ordinary. And you can see that they do form distinct regions within this plot. So then on the bottom right is a simulation of 3 asteroid compositions within these subclasses for a 2-week EPIX measurement. And the statistical uncertainties are excellent, and we can distinguish between these 3 compositions by measuring these gamma ray lines. You can also use the neutron measurements to determine the abundance of water, which is shown the epithermal counting rate versus thermal plus epithermal counting rate on the lower left plot. And there's this linear trend where decreasing, going down to the lower left is actually an increase in hydrogen. And the amount of water that is present in these primitive bodies can be related to where that primitive body was formed within the solar system. This is a simulated mission concept for a landed lunar mission where you use a single module of EPIX. And you can use the detection of key gamma ray lines to classify rock types. So for example, on the right plot is iron versus magnesium. Then the diamonds correspond to a 12-hour EPIX measurement, and all the colored circles correspond to different types of lunar material. And we can clearly distinguish between different types of lunar material and be able to classify rock types relevant to these Apollo samples. You can also use the neutron measurements to understand lunar hydrological cycling by looking for enrichments in hydrogen or looking for diurnal variability in hydrogen, and then assessing in situ resource utilization, such as looking for water, thorium and uranium, or magnesium, for example. So to summarize, planetary nuclear spectroscopy is a common technique that's been used to study the near-surface composition of planetary bodies. It can help address questions such as the presence and abundance of hydrogen, planetary structure, origin, and evolution, and in situ resource utilization. The EPIX instrument that's under development at LANL is a low-resource combined gamma ray and neutron spectrometer for future missions. It utilizes alpacylate scintillator and silicon photomultipliers for readout to achieve reduced size, weight, power, and instrument complexity relative to previous planetary nuclear spectroscopy instruments. And its modularity makes this instrument design accessible to different mission platforms, including CubeSats and balloons. So with that, thank you, and please feel free to reach out with any questions or comments.